Yes, the table 450.3b values for primary-only protection, which includes 125% for I greater than 9 amps, 167% for I less than 9 amps, and 300% for I less than 2 amps, can be used for primary fuse sizing. Subsequently, the secondary fuse size can be determined using 125% and 167% as applicable. Table 450.3b offers the minimum primary fuse size necessary to safeguard a transformer against damage resulting from overcurrent scenarios. This table takes into account the transformer's rated current and the highest fault current it can endure. After determining the primary fuse size, you can proceed to select the secondary fuse size. The secondary fuse size should ideally be 125% of the primary fuse size when the current is greater than 9 amps and 167% when the current is less than 9 amps. This approach helps ensure that the secondary fuse trips or blows before the primary fuse, thus shielding the transformer from potential harm. Let's consider an example. Suppose we have a transformer characterized by a rated current of 10 amps and a maximum fault current of 100 amps. Referring to table 450.3b, we would choose a primary fuse size of 15 amps, calculated as 125% of 10 amps. Consequently, a secondary fuse size would be 18.75 amps, obtained by taking 125% of 15 amps. This fuse configuration guarantees that the transformer remains protected from damage should an overcurrent event occur. The primary fuse will trip first, mitigating potential harm to the transformer, and the secondary fuse will then trip, isolating the transformer from the fault. To elaborate further on transformer protection and fuse sizing, it is important to understand the roles of both primary and secondary protection. The primary protection is the first line of defense against overcurrents originating from the source side, while the secondary protection safeguards against overcurrents originating from the load side. Proper coordination between these two protective devices is crucial for effective transformer protection. When selecting fuse sizes, one must consider several factors including the transformer's kV-ampere rating, primary and secondary voltages, and the expected load characteristics. Overfusing can lead to inadequate protection, potentially damaging the transformer during fault conditions. On the other hand, underfusing can cause nuisance tripping, disrupting power supply. In the example provided, the transformer has a rated current of 10 amps, which means it's designed to safely handle 10 amps under normal operating conditions. The maximum fault current of 100 amps indicates the highest current the transformer can withstand during a short circuit or fault before sustaining damage. Table 450.3b provides guidance on selecting the appropriate primary fuse size based on these parameters. The 125% multiplier for currents greater than 9 amps allows for some overload capacity without causing the fuse to blow prematurely. This is important because transformers often experience temporary overloads during startup or when supplying fluctuating loads. However, the fuse must still be able to trip quickly enough to protect the transformer during a severe fault. The secondary fuse, sized at 125% of the primary fuse, provides additional protection on the load side. This ensures that any faults originating from the load side are cleared before they can propagate back to the transformer and cause damage. The coordination between the primary and secondary fuses is essential for selectivity. Selectivity means that the fuse closest to the fault should trip first, minimizing the impact on the rest of the electrical system. In this case, the secondary fuse is designed to trip before the primary fuse for faults on the load side, while the primary fuse will trip first for faults on the source side or within the transformer itself. The selection of fuse types is also an important consideration. There are various types of fuses available, each with its own characteristics in terms of current carrying capacity, interrupting rating, and time current curves. The interrupting rating of the fuse must be sufficient to safely interrupt the maximum fault current available at its location. Time current curves describe the relationship between the current flowing through the fuse and the time it takes for the fuse to trip. These curves are used to coordinate fuses and other protective devices in the electrical system. In addition to fuses, Circuit breakers can also be used for transformer protection. Circuit breakers offer the advantage of being resettable, which can reduce downtime in the event of a fault. However, circuit breakers typically have higher interrupting ratings and more complex coordination requirements than fuses. When using circuit breakers for transformer protection, it is important to select breakers with appropriate time current characteristics and to coordinate them with other protective devices in the system. Furthermore, it is critical to adhere to the National Electrical Code, or NEC, requirements when sizing and installing transformer protection devices. The NEC provides specific guidelines on fuse and circuit breaker sizing, conductor ampacity, and grounding requirements for transformers. Compliance with the NEC ensures that the transformer is protected against overcurrents, short circuits, and ground faults, minimizing the risk of fire and electrical hazards. In summary, transformer protection involves a comprehensive approach that considers the transformer's characteristics, the expected load conditions, and the applicable codes and standards. Proper fuse or circuit breaker sizing, coordination, and installation are essential for ensuring the reliable and safe operation of transformers. The Table 450.3b is an important guide for determining the minimum primary fuse size required to protect a transformer. When sizing the secondary fuse, you want it to coordinate with the primary so the secondary fuse clears faults on the secondary side before the primary fuse operates. Always consult with a qualified electrical engineer or electrician to ensure that the transformer protection system is properly designed and installed. NEC Article 450 covers transformers in detail. The primary and secondary protection scheme described is only one way to protect the transformer. There are other ways to achieve transformer protection. The specific application will dictate the means of protection. For example, a transformer may be protected with an overcurrent relay communicating with a circuit breaker. Large transformers are generally protected using more sophisticated methods. The example given previously uses fuses only, and the NEC allows for this type of protection scheme. The 125% and 167% values are important for proper coordination between the primary and secondary protection. The coordination is designed to isolate the fault to the immediate area rather than cause an outage to the entire system. Overcurrent protection is required on the primary and secondary sides of a transformer rated more than 600 volts nominal. If the primary side overcurrent protection also provides overcurrent protection to the secondary side, overcurrent protection is not required on the secondary side. The overcurrent device on the primary side needs to comply with Table 450.3 of 450.3b. If the transformer is a control transformer, using Table 450.3c is applicable. For a transformer rated 600 volts or less, overcurrent protection is required on the primary and secondary. As before, if the primary overcurrent device provides overcurrent protection on the secondary side, overcurrent protection is not required on the secondary side. In general, the overcurrent protection is intended to protect the transformer from overload and fault currents. Overload conditions are generally long-term and will cause the transformer to overheat. Fault currents are short-term and can be disruptive to the transformer if they are not cleared quickly. When selecting the overcurrent protection, it is important to consider the inrush current of the transformer. Inrush current is a high current that flows when the transformer is initially energized. The inrush current can be several times the normal operating current of the transformer. The overcurrent protection must be able to withstand the inrush current without tripping. Typically, time delay fuses are used for transformer protection due to their ability to ride through temporary overloads such as inrush currents without opening the circuit. This prevents nuisance tripping, which can be a common issue if fast-acting fuses are used. The time delay characteristic allows the fuse to differentiate between a temporary surge and a sustained overload or short circuit condition. For transformers rated over 600 volts, the primary overcurrent protection, according to Table 450.3a, depends on whether the transformer has a circuit breaker on the secondary side. If there is no secondary circuit breaker, the primary overcurrent device can be set at 300% for transformers with a rated impedance of not more than 6%, or 250% for transformers with a rated impedance of more than 6%. If there is a secondary circuit breaker, the primary overcurrent device can be set at 125%. These percentages are relative to the transformer's rated primary current. For transformers rated 600 volts or less, Table 450.3b provides guidance. If the primary current is greater than 9 amps, the overcurrent protection device can be set at 125% of the primary current. If the primary current is less than 9 amps, the overcurrent protection device can be set at 167% of the primary current. If the primary current is less than 2 amps, the overcurrent protection device can be set at 300% of the primary current. It's also important to note that the next higher standard overcurrent device rating is permitted if the calculated value does not correspond to a standard size. The secondary overcurrent protection, when required, should be sized to protect the secondary conductors and the transformer itself. The NEC provides guidelines for sizing secondary conductors based on the transformer's secondary current rating. The overcurrent protection should be sized no larger than the ampacity of the secondary conductors. In addition to overcurrent protection, transformers should also be protected against ground faults. Ground faults can occur when a phase conductor comes into contact with a grounded surface. Ground fault protection can be provided by a ground fault relay or a ground fault circuit interrupter. Ground fault relays are typically used for larger transformers, while ground fault circuit interrupters are used for smaller transformers. The location of the transformer also affects the type of protection required. For example, transformers installed in hazardous locations require special protection to prevent explosions or fires. Transformers installed outdoors must be protected against weather conditions such as rain, snow, and ice. Periodic inspection and maintenance of transformer protection devices are essential to ensure their proper operation. Fuses should be inspected for signs of damage or deterioration, and circuit breakers should be tested to verify their trip settings. Regular maintenance can help prevent transformer failures and ensure the safety of the electrical system. The term impedance refers to the opposition to the flow of alternating current in an electrical circuit. In a transformer, impedance is primarily determined by the inductance of the windings. A higher impedance generally means a greater voltage drop across the transformer under load, which can affect voltage regulation. The rated impedance of a transformer is usually expressed as a percentage of the transformer's base impedance. This percentage indicates the voltage drop from no load to full load conditions. Transformers with lower impedance values are generally more efficient and have better voltage regulation, but they may also be more susceptible to damage from high fault currents. Conversely, transformers with higher impedance values offer better protection against fault currents, but they may have poor voltage regulation and lower efficiency. The Table 450.3 in the NEC differentiates between transformers with impedance not more than 6% and those with impedance more than 6% because the impedance affects the magnitude of fault current that the transformer can deliver. Transformers with lower impedance can deliver higher fault currents, which is why the overcurrent protection requirements are more stringent. The 300% and 250% values mentioned earlier for primary overcurrent device settings reflect this difference in fault current capability. The purpose of limiting the overcurrent protection to these percentages is to ensure that the transformer is protected from damage due to excessive fault currents. The selection of the appropriate impedance value for a transformer depends on the specific application. Factors to consider include the voltage regulation requirements, the available fault current, and the desired level of protection. In some cases, it may be necessary to use a transformer with a higher impedance to limit the fault current and protect downstream equipment. In other cases, a transformer with a lower impedance may be preferred to improve voltage regulation and efficiency. The Table 450.3b in the NEC uses different current thresholds, such as greater than 9 amps, less than 9 amps, and less than 2 amps. to determine the allowable overcurrent protection settings for transformers rated 600 volts or less. These thresholds are based on the typical operating characteristics of small transformers and the need to provide adequate protection without causing nuisance tripping. The higher percentage values allowed for lower current transformers, such as 167% and 300%, reflect the fact that these transformers are less likely to experience high fault currents and can tolerate higher overloads for short periods of time. The 125% value for transformers with primary currents greater than 9 amps is a more conservative setting that provides better protection against both overloads and fault currents. The use of these different thresholds allows for a more tailored approach to transformer protection, ensuring that the overcurrent protection is appropriate for the specific transformer and its application. Controlled transformers, as mentioned earlier, are small transformers used to supply power to control circuits in industrial and commercial equipment. These transformers typically have low kVA ratings and are designed to provide a stable voltage for controlled devices such as relays, contactors, and timers. The Table 450.3c in the NEC provides specific overcurrent protection requirements for control transformers. Because control transformers are often subjected to frequent starting and stopping of controlled devices, they may experience high inrush currents. The overcurrent protection for control transformers must be able to withstand these inrush currents without tripping, while still providing adequate protection against overloads and fault current. The NEC allows for higher overcurrent protection settings for control transformers than for general-purpose transformers, reflecting the unique operating characteristics of these devices. In addition to fuses and circuit breakers, other types of protective devices can be used for transformer protection, such as overcurrent relays, differential relays, and sudden pressure relays. Overcurrent relays are used to detect overloads and fault currents and can be programmed to trip a circuit breaker or other interrupting device. Differential relays are used to detect internal faults within the transformer and can provide very sensitive and fast protection. Sudden pressure relays are used to detect rapid increases in pressure within the transformer, which can indicate an internal arc or other fault condition. These relays are typically used for larger transformers where the consequences of a failure are more severe. The selection of the appropriate protective devices for transformer depends on several factors, including the transformer's size, voltage rating, importance, and the potential consequences of a failure. A comprehensive protection scheme may include a combination of different types of protective devices to provide multiple layers of protection. Effective grounding is also crucial for transformer protection. A properly grounded transformer can help to limit the magnitude of ground fault currents and reduce the risk of electric shock. The NEC provides detailed requirements for grounding transformers, including the size and type of grounding conductors, the location of grounding electrodes, and the bonding of metallic enclosures. Grounding should be performed in accordance with the manufacturer's instructions and the applicable codes and standards. Regular testing and maintenance of the grounding system are essential to ensure its effectiveness. The NEC also addresses the location and installation of transformers. Transformers should be installed in a well-ventilated area to prevent overheating. They should be protected from physical damage and should be accessible for inspection and maintenance. Transformers installed in hazardous locations must comply with the special requirements for those locations. The NEC provides specific guidelines for the installation of transformers in various types of occupancies, such as commercial buildings, industrial plants, and residential dwellings. These guidelines are designed to ensure the safety of people and property. Proper labeling of transformers is also important. Transformers should be clearly labeled with their voltage rating, kVA rating, impedance, and other important information. The labeling should be durable and easily readable. Warning signs should be posted to alert personnel to the potential hazards associated with transformers. In summary, transformer protection is a complex topic that requires a thorough understanding of electrical principles, codes, and standards. Proper fuse or circuit breaker sizing, coordination, and installation are essential for ensuring the reliable and safe operation of transformers. A comprehensive protection scheme may include a combination of different types of protective devices to provide multiple layers of protection. Protective grounding, proper location, and clear labeling are also important considerations. Consulting with a qualified electrical engineer or electrician is recommended to ensure that the transformer protection system is properly designed and installed. The transformer's nameplate provides critical information for determining the appropriate overcurrent protection. This includes the kV ampere rating, primary and secondary voltages, and impedance. This information is essential for calculating the transformer's rated currents and selecting the correct fuse or circuit breaker sizes. The ambient temperature also affects the transformer's ability to dissipate heat. Transformers installed in high ambient temperature environments may require derating of their kV ampere capacity or the use of additional cooling measures. The NEC provides guidelines for derating transformers based on ambient temperature. The altitude at which the transformer is installed can also affect its performance. Transformers installed at high altitudes may experience reduced dielectric strength due to the lower air density. Special considerations may be required for transformers installed at high altitudes. The type of load served by the transformer also affects the type of protection required. Transformers serving nonlinear loads, such as electronic equipment, may require special protection to prevent overheating and harmonic distortion. Harmonic filters may be necessary to mitigate the effects of nonlinear loads. The maintenance of transformers is essential to ensure their long-term reliability and performance. Regular inspections should be performed to check for signs of oil leaks, corrosion, or other damage. The transformer's bushings, tap changers, and other components should be inspected and cleaned as necessary. The transformer's oil should be tested periodically to check for moisture, acidity, and other contaminants. The oil should be replaced or reconditioned if necessary. The transformer's cooling system should be inspected and maintained to ensure that it is functioning properly. The transformer's connections should be checked for tightness and corrosion. All protective devices should be tested and calibrated regularly. Proper maintenance can help to prevent transformer failures and extend the life of the transformer. In addition to the NEC, other standards and guidelines provide information on transformer protection. The Institute of Electrical and Electronics Engineers, or IEE, publishes a number of standards on transformer protection, including IEE Standard C37.91, IEE Guide for Protective Relay Applications to Power Transformers. The National Fire Protection Association, or NFPA, publishes NFPA 70B, Recommended Practice for Electrical Equipment Maintenance, which provides guidance on the maintenance of transformers and other electrical equipment. These standards and guidelines provide valuable information for engineers and technicians involved in the design, installation, and maintenance of transformer protection systems. A transformer's thermal overload capability refers to its ability to withstand temporary overloads without sustaining permanent damage. The thermal overload capability is determined by the transformer's design and the materials used in its construction. The transformer's nameplate typically includes information on its thermal overload capability. The overcurrent protection should be coordinated with the transformer's thermal overload capability to prevent damage from prolonged overloads. The use of temperature sensors and thermal relays can provide additional protection against overloads. These devices can be used to monitor the transformer's temperature and trip a circuit breaker or other interrupting device if the temperature exceeds a safe limit. The installation of a transformer requires careful planning and execution. The transformer should be located in a safe and accessible location. The transformer should be properly supported and secured to prevent movement. The transformer's connection should be made in accordance with the manufacturer's instructions and the applicable codes and standards. The transformer should be grounded in accordance with the NEC requirements. The transformer should be tested and inspected before being energized. Proper installation is essential to ensure the safe and reliable operation of the transformer. The selection of a transformer should be based on the specific application requirements. Factors to consider include the load requirements, the voltage requirements, the efficiency requirements, and the environmental conditions. The transformer should be sized appropriately for the load. A transformer that is too small will be overloaded and may overheat. A transformer that is too large will be inefficient and may have poor voltage regulation. The transformer should be selected to operate efficiently under the expected load conditions. The transformer should be suitable for the environmental conditions in which it will be installed. The use of energy-efficient transformers can save significant amounts of energy over the life of the transformer. Energy-efficient transformers are designed to minimize losses and operate at higher efficiencies. The initial cost of an energy-efficient transformer may be higher, but the long-term energy savings can offset the initial cost. The purchase of energy-efficient transformers can also qualify for rebates and incentives from utility companies. The disposal of transformers requires special handling due to the presence of hazardous materials, such as oil and polychlorinated biphenyls, or PCBs. Transformers containing PCB must be disposed of in accordance with the Environmental Protection Agency, or EPA, regulations. The oil from transformers should be recycled or disposed of properly. The metallic components of transformers can be recycled. Proper disposal is essential to protect the environment. Power quality issues can also affect transformer performance and protection. Voltage sags, voltage swells, and harmonic distortion can cause transformers to overheat and fail. The use of power quality monitoring equipment can help to identify and mitigate power quality issues. The installation of power quality filters can reduce harmonic distortion. The use of voltage regulators can stabilize voltage fluctuations. Addressing power quality issues can improve transformer performance and extend its life. Transient voltage surges caused by lightning strikes or switching events can damage transformers. The use of surge arresters can protect transformers from transient voltage surges. Surge arresters are designed to divert the surge current to ground, protecting the transformer from damage. Surge arresters should be installed on both the primary and secondary sides of the transformer. The proper selection and installation of surge arresters are essential for protecting transformers from transient voltage surges. Understanding transformer connections is essential for proper operation and protection. Transformers can be connected in various configurations such as delta-delta, delta-Y, Y-delta, and Y-Y. The connection configuration affects the voltage and current relationships on the primary and secondary sides of the transformer. The connection configuration also affects the transformer's ability to handle unbalanced loads and harmonic currents. The proper connection configuration should be selected based on the specific application requirements. The NEC provides guidelines for connecting transformers in various configurations. Transformer testing is an important part of ensuring reliable operation. Routine tests include insulation resistance tests, turns ratio tests, and polarity tests. More comprehensive tests include impedance tests, excitation current tests, and short-circuit tests. These tests can identify potential problems with the transformer before they lead to failure. Regular testing and maintenance can significantly extend the life of a transformer. Transformer noise can be a concern in some applications. Transformer noise is caused by the vibration of the transformer core and windings. The amount of noise produced by a transformer depends on its size, design, and operating conditions. Noise reduction measures can be taken to minimize transformer noise. These measures include the use of vibration isolation pads, sound barriers, and noise-canceling transformers. The selection of a low-noise transformer can also reduce noise levels. Transformer fire protection is an important consideration, especially for transformers installed indoors. Transformers containing flammable oil should be protected with fire suppression systems. Fire suppression systems can include automatic sprinklers, carbon dioxide systems, and dry chemical systems. The selection of the appropriate fire suppression system depends on the size and location of the transformer. The NEC provides guidelines for transformer fire protection. Transformer efficiency is an important factor to consider when selecting a transformer. Transformer efficiency is the ratio of the output power to the input power. High-efficiency transformers waste less energy and have lower operating costs. Transformer efficiency is affected by factors such as core material, winding design, and operating temperature. Energy-efficient transformers are typically more expensive, but they can save significant amounts of energy over their lifespan. Transformer loading is the amount of power that a transformer is supplying to a load. It is important to ensure that a transformer is not overloaded, as this can lead to overheating and failure. Transformer loading is typically expressed as a percentage of the transformer's rated capacity. A transformer should be sized to handle the expected load, with some margin for future growth. Proper transformer loading can help to extend the life of the transformer and improve its reliability. Transformer life expectancy depends on several factors, including the design, manufacturing quality, operating conditions, and maintenance practices. Well-maintained transformers can last for many years, even decades. Factors that can shorten transformer life include overloading, overheating, moisture, and contamination. Proper maintenance and operating practices can help to extend transformer life. Consider safety features such as pressure relief valves and temperature monitoring systems to enhance transformer safety and prevent catastrophic failures. Always adhere to local electrical codes and regulations when installing and maintaining transformers. These codes are in place to protect people and property from electrical hazards. The specific code requirements may vary depending on your location, so it is essential to consult with local authorities or qualified electricians.